Welcome back to Physics 191. I'm Gerard Blanchard. Last time we worked a kinematic situation with a brick sliding off of a roof. We're going to revisit that situation with another exercise. But before I do that, I would like to remind you once again about my suggestions about how to use these videos to help you learn physics. I would like you to try to work these exercises, try and stay ahead of me. If you get stuck, that's okay, because probably something I'll say a little bit later on will get you unstuck, and once you get to that point, it'd be a good idea if you've recorded this television show or if you're watching this online to pause once again, and once you've gotten unstuck, try to work ahead. Try to work ahead of me. Once you're able to work ahead of me, you know that you understand what's going on. These are very complicated situations, I understand that, and it's only a matter of practice that'll help you develop your skill. Well, let's revisit the last situation that we had, where we had a brick sliding down an icy roof with no friction, but now we're going to introduce friction. The statement of the exercise is, a brick of mass 1.0 kilograms slides down a roof inclined at 30 degrees with respect to the horizontal. The coefficient of friction between the roof and the brick is 0.2. If the brick starts from rest, how fast is it moving 0.9 seconds later, which is exactly the same as we had last time, except now that we've introduced friction. Go ahead and try. See what you can do with this exercise. Model the exercise and see what you can do. Okay, let's draw our diagram. I'll draw it the same way I did last time. We have a brick sliding down a roof. We have T initial is equal to 0 seconds. Vx initial is equal to 0 meters per second. T final is 0.9 seconds. Vx final, we don't know, and just like last time, I'm going to make that my x-axis, the roof. We have 30 degrees right here. We have to draw in our forces on the brick. We have weight, which was 1 times 9.8. Our weight is 9.8 newtons, and that of course is weight equals mass times g. We have the normal force. And now we have to add in friction. Kinetic friction. And we know that the friction is going to be parallel to the roof. Just as the normal force is always perpendicular to the roof, the friction is going to be parallel to the roof. It's going to oppose the motion. And we also know that kinetic friction is equal to the coefficient of kinetic friction times the normal force, which gives us, since we know the coefficient of kinetic friction, we know that the kinetic friction force is going to be 0.2 times the normal force. Now, it's not 0.2 newtons. We have to realize that that's 0.2 times the normal force. We have to draw in our y-axis. To do that, I'll tilt the page so that x-axis is horizontal. Draw in our y-axis. being vertical now. And we know that we'll have to break up weight into a horizontal and a vertical component, with this being a 60-degree angle. We have weight in the x direction is equal to weight adjacent to the angle, and weight in the y direction would be minus weight opposite to our 60-degree angle. This is exactly the same as we did last time, except now that we've added in our kinetic friction force. Turn my diagram again. And we have to write our starting equations. Well, we're going to have 3 this time. We have, just as last time, x kinematic, which would be ax is equal to Vx final minus Vx initial over T final minus T initial. We have our x non-equilibrium equation, which is that Ax is equal to force total x over mass. And now we have to add in an equation for y. Well, you might not realize that right away, but what you would realize is that if you started working this just like we did last time, you would have too many unknowns and you would need another equation. Well, we do have another equation, and that is our y equation. We have to ask ourselves, do we have equilibrium in y, or do we have non-equilibrium in y? Well, as we've drawn our y-axis, it's perpendicular to the roof. The brick is not moving perpendicular to the roof, and it stays not moving perpendicular to the roof. So, as far as the y is concerned, the brick is at rest in y, and it stays at rest in y. So we have y equilibrium. So we have to draw in our y equilibrium equation, which would be force total y is equal to 0. Those are our starting equations. So now we have completely modeled the situation. We have our diagram, we've listed all of our knowns and unknowns, we've drawn in our forces, and we've identified the type of situation, and we've written down our starting equation. So this is our complete model of this situation. Now it's just a matter of algebra. Well, let's get started. Ax, we don't know. Ax is equal to Vx final. We don't know that either. That's what we're looking for. Vx final minus Vx initial. That we do know. That's 0. Divided by T final. T final is 0.9 seconds minus T initial, which is 0. Well, that's one equation with 2 unknowns, and once again, it comes out to be 0.9 Ax is equal to Vx final. So we're stumped for the moment. As far as this equation is concerned, we have to move on to our next equation, which happens to have Ax in it, so that's good so far. Ax, we don't know, is equal to the total force in the x direction. What forces do we have pulling in the positive x direction? Weight, not all of it, but part of it. Weight adjacent is pulling in the positive x direction. Pulling in the negative x direction is our friction force, minus F kinetic. And that is the total force in the x direction. Divide that by the mass of the brick. Mass of the brick is 1 kilogram. We can work with this a little bit more. Let's see what we can get out of this. We have Ax is equal to weight adjacent. Weight adjacent is weight times the cosine of our 60-degree angle minus our kinetic friction force, which we know is 0.2 times the normal force. Once again, that's not 0.2 newtons. Be careful. Actually, when I originally wrote up here, this should actually be 0.2 times the normal force. 0.2 times the normal force divided by 1. Well, we don't need to write in divided by 1 since that doesn't change anything. And finally, we can write AX is the weight of 9.8 newtons cosine of 60 degrees minus 0.2 times the normal force. So once again, we're in the situation where we have an equation with two unknowns in it. Actually, if we take both of these equations together, we have two equations with three unknowns. We have two equations, but we have AX, VX final, and the normal force as our unknowns. Let's hope that our Y equation will be able to help us. In fact, it will. Our Y equation will give us the normal force, which will give us AX, which will give us VX final. Let's work with our Y equation. Force total Y is equal to 0. What forces do we have in the positive Y direction? That's normal force. Force total Y is the normal force. What do we have in the negative Y direction? That was weight opposite. So minus, normal force minus weight opposite is equal to 0, or normal force is equal to weight opposite, or normal force is equal to weight times the sine of our 60-degree angle. Okay, my equations are going to start to run into each other, so I'll put a little dividing line in here. And that tells us that the normal force is equal to 9.8 sine of 60 degrees, or my normal force, 9.8 times sine of 60 degrees is 8.49 newtons. 8.49. So my normal force is 8.49 newtons. That's what we needed. That was our key, because now we can take that 8.49 newtons, put it into this equation, find AX, take AX, put it into here, and solve for VX final. So we're nearing the end here. We almost have it. AX is equal to 9.8 cosine 60 degrees minus 0.2 times 8.49. That will give us AX. 9.8 times cosine of 60 minus 0.2 times 8.49. That gives us an acceleration of 3.20 meters per second squared. 3.20 meters per second squared. And so finally we can find Vx final. So we have 0.9 times 3.20 is equal to Vx final, or .9 times 3.2, 2.88. 2.88 meters per second is equal to Vx final. And we've answered that question. So this is a skill that we're trying to develop through practice. It's not something that you can memorize. Now, let's go on. We've hinted about position, where an object is. Let's add that into our kinematic equations. Position is also a vector. The position vector, we write that with a lowercase r, vector, but the components of the position vector are just x and y, which would make the magnitude of the position vector the distance that the object is from the origin. Position is measured in length units or units of meters. How does position relate to the things that we've been talking about so far, acceleration and velocity? Well, velocity is the change in position divided by the change in time, or to be a little bit more specific, the average velocity vector of an object is equal to the change in its position vector divided by the change in time. And so that is going to be another kinematic equation for us. Average velocity vector is equal to change in position vector divided by change in time. And since that's a vector equation, it's two component equations. The average velocity of an object in the x direction is equal to the change in its x position divided by the change in time. Or if we expand that out, the average velocity in x is equal to x final minus x initial, all of that divided by t final minus t initial. And we have the same equation for y. Average velocity in the y direction is equal to y final minus y initial divided by t final minus t initial. Now, why have I been specifying average velocity? Well, in the situations that we've already seen, velocity has changed, so velocity doesn't have just one value in these situations. The velocity is changing, and this equation in particular, this equation refers to the average velocity of the object in particular. So it's important to remember that is the average velocity vector that is equal to the change in position vector divided by the change in time. And that brings us into our next chapter, which is motion with a changing velocity, and where we'll get into our other three kinematic equations that I've told you about. Okay, let's take that equation that I just introduced. Average velocity is equal to change in position vector divided by change in time, which is our two component equations for x and y. Now, if the acceleration is constant, then we can calculate the average velocity by taking the average of the initial and the final velocity. Or in other words, v vector average is equal to v vector final plus v vector initial divided by 2. That's how we take an average. We add things together and divide by 2. Be careful of that plus sign. It's a common mistake to put a negative sign in there. We're not taking the difference of initial and final velocity in this equation. We're averaging them, which means that we have to add them together and divide by 2. So, once again, if acceleration is constant, then the average velocity vector is just the average of the final and the initial, or v final vector plus v initial vector divided by 2, which is two component equations. The average velocity in the x direction is vx final plus vx initial divided by 2, and the average velocity in the y direction is vy final plus vy initial divided by 2. Or if we combine the top and the bottom equations, then both of those have vx average x in them or v average y in them, then we can write another equation, which is Vx final plus Vx initial divided by 2 equals x final minus x initial divided by t final minus t initial. Combining our two y equations gives us Vy final plus Vy initial divided by 2 equals y final minus y initial divided by t final minus t initial. And this is going to be our second set of kinematic equations. Now, I did stipulate that these equations are valid if acceleration is constant. And in Physics 191, the acceleration will always be constant, or at least piecewise. What I mean by that is we can always break up our situation into pieces of time, into blocks of time where the acceleration is constant. That is actually what makes this Physics 191, which is algebra-based physics, as opposed to calculus-based physics. If we were allowed the acceleration to change continuously, we would need calculus to answer some of the questions that come up. But in algebra-based physics, which is what Physics 191 is, the acceleration will always be, as I said, at least piecewise constant, meaning that we can break up any situation into pieces of time with constant acceleration. So these equations will be valid at least for a piece of time. We can break up our situation into discrete pieces of time when these equations will apply. And that brings us to our second general equation for a kinematic situation. So, kinematic situation, how do we identify? A kinematic situation deals with either acceleration or velocity or position and time. Our second general equation for kinematic situations, actually it's a pair of equations, would be Vx final plus Vx initial divided by 2 is equal to x final minus x initial divided by t final minus t initial. And the reason why that's an equation is that both of those are equal to the average velocity. And for y, Vy final plus Vy initial divided by 2 equals y final minus y initial divided by t final minus t initial. And once again, the way to remember this equation is that both sides of that equation are equal to average velocity. We can take our two kinematic equations that we have so far and make more kinematic equations. The two kinematic equations that we have so far are Ax is equal to Vx final minus Vx initial divided by t final minus t initial, and Vx final plus Vx initial divided by 2 equals x final minus x initial divided by t final minus t initial. If we take the left-hand side of that second equation and multiply it by the right-hand side of the first, then we would have the quantity Vx final minus Vx initial divided by t final minus t initial times the quantity Vx final plus Vx initial divided by 2 equals the left-hand side of the first equation times the right-hand side of the second. Or Ax is equal to Ax times x final minus x initial over t final minus t initial. Now that's still an equation because each time we've multiplied by the same thing, or things that were equal. If we multiply both sides by t final minus t initial, and also multiply both sides by 2, we get Vx final minus Vx initial quantity times the quantity Vx final plus Vx initial equals 2 times Ax times x final minus x initial. If we work out the algebra a little bit more, and I recommend that you do that as an exercise, we get finally Vx final squared minus Vx initial squared equals 2Ax times x final minus x initial. So that is another valid kinematic equation. What's the point? Why do we do this? Well, what you'll see is that we've eliminated time. We have Vx final, we have Vx initial, we have Ax, and we have position, but time doesn't appear in this equation. So this is an equation that we can use when we don't have time, when we don't have any information on time, and we don't need to know time. So, coming back to kinematic situations, a kinematic situation deals with either acceleration or velocity or position and time, and we have our third kinematic equation. Our third kinematic equation is Vx final squared minus Vx initial squared equals 2 times Ax times x final minus x initial. And we could have done exactly the same thing with y, and we would get exactly the same equation with y in place of x, and that gives us Vy final squared minus Vy initial squared equals 2Ay times y final minus y initial. So this is our third kinematic equation in which we've eliminated the need to know time. We're going to do this one more time for our fourth equation. You might be able to guess that what we're going to do is we're going to eliminate Vx final and Vy final. And that is what we're going to do. We're going to take our two starting equations that we had before. Ax is equal to Vx final minus Vx initial divided by T final minus T initial. And also Vx final plus Vx initial divided by 2 is equal to x final minus x initial divided by T final minus T initial. And we're going to solve the first equation for Vx final. And if we do that, then we get that Vx final is equal to Vx initial plus Ax times T final minus T initial. That is the top equation solved for Vx final. And once again, I would recommend that you do this as an exercise to prove to yourself that that is the case. We're going to take Vx final from that equation and put it into the second equation. And that gives us x final minus x initial over T final minus T initial is equal to Vx initial plus Ax times T final minus T initial plus Vx initial divided by 2. If you work that out, and I do recommend that you do that, as an intermediate step you would get x final minus x initial divided by T final minus T initial is equal to Vx initial plus 1/2 Ax times T final minus T initial. Multiplying both sides by T final minus T initial gives us, finally, x final minus x initial equals Vx initial times T final minus T initial plus 1/2 Ax times T final minus T initial squared. And I do recommend that you work through the algebra on this to prove to yourself that it's all correct. That equation at the bottom is our fourth kinematic equation where we've eliminated Vx final. So, in kinematic situations, which is a situation that deals with acceleration or velocity or position and time, we have our fourth kinematic equation, which is the change in x, or x final minus x initial, is equal to whatever velocity we had initially, Vx initial, times the change in time, times t final minus t initial, plus 1/2 of the acceleration times the change in time squared, or x final minus x initial is equal to Vx initial times t final minus t initial plus 1/2 Ax times t final minus t initial squared, and the same for y. Y final minus y initial is equal to Vy initial times t final minus t initial plus 1/2 Ay times t final minus t initial squared. So, let's bring that all together. In kinematic situations, we have 4 different starting equations to choose from. And they would be that Ax is equal to the change in Vx divided by the change in time, or the average velocity, Vx final plus Vx initial divided by 2 equals the change in x over the change in time, or Vx final squared minus Vx initial squared equals 2Ax times the change in x, or the change in x is equal to Vx initial times the change in time plus 1/2 Ax times the change in time squared. Each of these equations leaves out one of our kinematic variables. The top one, Ax is equal to change in Vx over change in time, doesn't have position in it. Our second, Vx final plus Vx initial divided by 2 equals the change in x over the change in time, doesn't have acceleration in it. Vx final squared minus Vx initial squared equals 2Ax times the change in x, doesn't have time in it. And finally, the change in x is equal to Vx initial times the change in time plus 1/2 acceleration in x times the change in time squared, doesn't have velocity, x final, doesn't have the final velocity in it. We have the same equations for y, where you just replace x with y. And to choose an equation to get started with, we choose the equation based on what we don't know and what we don't need to know. And also, we actually have 2 independent equations. We started from the acceleration is equal to change in velocity over change in time, and average velocity is change in x over change in time. Those are independent equations. So in any situation, we can use 2 separate equations for x and 2 separate equations for y per object. If we have multiple objects, we can use multiple equations. We're going to bring that all together and start solving exercises. In this question, an airplane lands and starts down the runway at a southwest velocity of 55 meters per second squared. What constant acceleration allows it to come to a stop in 1 kilometer? Draw a diagram, list your knowns and unknowns, identify the type of situation. Well, we have a change in velocity and a change in position. That's a kinematic situation. And you have to pick your starting equation. You have to pick your starting equation based on what you don't know and what you don't need to know. And what you don't know and don't need to know in this situation is time. You don't know how much time it takes to come to a stop, and you don't need to know time. You're not asked for time. So draw your diagram, list your knowns and unknowns, and also convert that 1 kilometer into basic metric units, and try to answer the question of what is the acceleration. I'll also give you a hint here. The southwest velocity, that's actually kind of a red herring. You don't need to worry about the fact that it's moving southwest, because we can make our x-axis be southwest. So you don't have to draw anything special for southwest. We'll just have it moving in x. So please draw your diagram, list your knowns and unknowns, identify this as a kinematic situation, and pick your proper starting equation. That's the real key for this exercise, and answer the question. Let's draw our runway. We'll make that the x-axis. We have our airplane. And our x-axis, we'll call that southwest, since that's what the exercise told us. We have initially, T initial is 0. The Vx is 55 meters per second. That's Vx initial, Vx initial is 55 meters per second. X initial, we'll call that 0. We're always free to pick where our 0 of position is. Just as we're always free to pick when we start our stopwatch to start time, we're also free to pick where our origin is, where 0 position is. So Vx initial is 0 meters. So seconds, meters per second, and 0 meters. At the end, T final, we don't know. Vx final, we know is 0. It comes to a rest. And x final is 1.0 kilometers, which we have to convert to basic metric units, which is 1,000 meters is the same as 1 kilometer. So that's the same, so we're multiplying by 1. Kilometer and kilometer go away, and we have 1,000 meters. And AX, the acceleration that it has during this interval, is our unknown. So now we have analyzed the statement of the exercise. We've gotten all of the information that we can out of it. We've listed our knowns and our unknowns. We have a change in position, a change in velocity. This is a kinematic situation. And the question is, what starting equation do we choose? We choose that based on what we don't know and don't need to know. What we don't know and don't need to know is time. So we choose our starting equation that doesn't have time in it. And that's our third equation, which is Vx final squared minus Vx initial squared is equal to 2ax times x final minus x initial. And so now we have completely modeled this situation. We have a mathematical model. It's just a matter of using our algebra from here. Vx final is 0 squared minus Vx initial, 55 squared, is equal to 2ax times x final. X final is 1,000 meters minus 0. We can solve that for AX by dividing both sides by 2 and dividing both sides by 1,000. And we have minus 55 squared divided by 2 times 1,000 is equal to AX. Calculate that. $55 squared divided by 2 times 1,000 gives us an acceleration of negative 1.51 meters per second squared. Now, what does it mean that we have a negative acceleration? That means that the acceleration is pointed in the negative x direction, or in other words, its velocity in the x direction is becoming more negative. It went from being positive 55 to 0 meters per second in the x direction, which is a decrease. So we would expect the acceleration to represent that, and that would be a negative acceleration. If your velocity is changing in the negative direction, becoming more negative, then acceleration is negative. So our acceleration in this case is negative 1.5 meters per second squared, and we've answered the question. We'll work through more exercises next time. Until then, think physics.